Hello, everyone. Very nice to see you again. Welcome to the summer course, the Tankang University 2022. My name is Longjie Yang from Department of Mechanical Engineering, Tankang University. Today, I want to talk about the topic about the micro drone or micro air vehicle, MAV. Drone is a short name of the unmanned air vehicle. Right now, are very popular all over the world. But today, my topic about the drone or micro air vehicle will focus on the bionic type of drone. So we call it ornithopter. Ornithopter, I will mention that. In order to fly, the birds and insects attract people for a long time, even for thousands of years. If you look at the history of China and Greece, you will find some people have ever claimed to fabricate bird-like air vehicle for surveillance and to show people's heart desire for develop this kind of bionic air vehicle. So today I will focus on introduce the flapping wing or biomimic drone. So this is ornithopter, bird-like air vehicle or flapper. In 15th century, Leonardo da Vinci has ever sketched a design, at the left figure. This figure shows his hand draft about the flapping fly mechanism. In 1870, a French, Gustave Trouvé, he made a flapping wing or an ornithopter which is propelled by dynamite, explosive. Try to make the wing flapping and create a successful flight about 70 seconds. Of course, very short period of moment. And later on, another people, Pernod, he developed a rubber band power ornithopter for sale. Like a toy. Later on. So from the record of the late 19th century, most of the people who are the flight pioneer, actually, they are witness a number of adventure to start to emulate, try to learn the bird to fly. But most of them fail or even sacrifice. So for the people, their first dream about fly is learn from nature, learn from birds and insects. They try to, install a pair of wings and try to fly like a bird. But actually, what happened? In 20th century, most of the successful fly actually was done by fixed wing aircraft, fixed wing, not the flapping wing. So the Professor Richard Feynman, he ever say in his famous lecture in Infinitesimal Machinery, he say, one always look at biology as a kind of guide, even though it never invent the wheel. And even though we don't make flapping wing for aircraft, because we sort of a better way. We sort of the fixed wing way, fixed wing, not a flapping wing. So even for Feynman, very famous physicist, he also initiated the field about the MEMS we talked about in the last hour. He also said flapping wing is not a good idea. So it is a good explanation about the pragmatism, I mean the practical principle. We hope they hope to make something useful and practical. When people developed artificial aircraft, finally they found Brother Wright. They developed the fixed wing aircraft and created a new area to fly, very successful until to now. Right? Even for our commercial jet, Boeing 747 or Airbus 380. Fixed wing, right? No flapping, no flapping, just fixed wing and to fly. So in all China, there's a similar situation. In all China, there's an old guy, his name is Modi. Modi, he criticized another people, Lu Ban. Lu Ban is a person, he's a wood scratchman, and he made a flapping wing machine and can fly for several days. Of course, we don't know how he made it. But even though Lu Ban have ever reported his success about that, Modi challenged him. He said, okay, your design, the flapping wing, is not as useful as my chariot control stick. My chariot control stick only 3 inches long, but we can forward 5 tons of weight. But how about your flapping wing? You can only fly in the sky for nothing for transportation. So he just, he just joke. He just, nothing very important about the flapping wing. So whatever in the West or in the East world, a lot of people, they challenge about the flapping wing. But as the technology move forward, some situation also change. After the first Gulf War in the 1990s, Ornithopter, the flapping wing, they changed their fate. The bad function about the flapping mechanism maybe they're not used for transportation, but they are suddenly found and used by U.S. Army by their smart use of the ultra-short range surveillance. You mean that what is ultra-short range surveillance? You mean that it's very small, flapping wing like a bird, right? If we can really fly it, it looks like a bird. So when you apply in the battlefield, nobody knows it's true bird or another bird, or artificial bird. If it's an artificial bird, we can install some camera on board, and we can do some mission about the surveillance, and try to protect our soldiers inside the battlefield. We can find the enemy as early as possible. So at that time, DARPA is Defense Advanced Research Project Agency. That research center, the United States, he found a 3-year project about the MAV project. They just call for design where anyone can make artificial flyer less than 50 centimeter in the palm size, can make this kind of palm size, aircraft for military surveillance. Because, Defense Department in the United States, they have their need in the battlefield. This project is to inspire and create artificial flyer less than 15 centimeter in size for military surveillance. And most of them at that time were categorized as a fixed wing or rotary wing, the conventional design, not a flapping wing. But one group, very special, one group that proposed to make flapping wing. Actually, that group is Caltech. Actually, The PI is Professor Yu Chang Tai. Actually, is the inventor. You know, if you have some memory about the micromotor, he invented the first micromotor in the world. He's one of the inventors. Dr. Tai, Yu Chang Tai of the Caltech, he cooperated with a company. Actually, that company right now very famous, Environment Incorporation. They cooperate together to develop first generation the flapping wing, called it Caltech Microbat. Let's see this video. Yeah, don't like this matter. So it's a pump size and 50 centimeter in size and only very, very light, probably about 10 grams. You can flap. You can remote control. So it's a flight test in South California. So it looks like a bird, but you can control, right? A remote control way. And you can see the feature very small, its size very small, so you can hardly see where it is. Even has some sounds, but you cannot exactly detect where it is. Okay, but at that time they have some problem about the endurance. It means that how long they can keep flying in the sky. So after the microbat, you know, why they can success? Why they can success? You know, the flapping wing MAV, this kind of drone, they can greatly compensate for the lack of the general lift of the fixed wing at a very slow speed. You know, for the fixed wing, his wing is fixed over there. It cannot flap. So he cannot fly in a very low speed. For example, hovering. Hovering is impossible. It must have some travel speed. But flapping wing, different. He can flap. Even this aircraft is stationarily hovering in the air, but because he can flap, so he can generate a thrust force, try to make it sustain in the air. So it's a very, very different one. So it's good for low speed or small space flight. Good for, just fly in between the lane, street, small street, indoors, outdoors, whatever. So DARPA liked this idea very much. So after 1999, DARPA support Caltech and the environment to develop pump-side flapping wing microbat. And thanks to the mobile phone technology, and the MEMS technology we mentioned in the last hour, microprocess chips, radio control chip, micro camera, wireless communication chip, pager motor, lithium battery, and whatever. All these small parts are fully available on the market. So you can try to integrate them together on this small micro air vehicle. So it is possible to integrate together. All of them thin, light, easily accessible. So not only the microbat, even in Netherlands, Technical University of Delft, they also developed their model, named as a Delft Flyer. Also very famous, especially in recent years. So many similar models have ever proposed and show off. And the next one, very, very smart one, amazing one, is Nano Hummingbird. This Nano Hummingbird is developed by Environment Corporation in 2011. It means that after the project about the microbat, Environment kept doing about the research by themselves, and then try to target on the hovering, like the hummingbird, hovering mission. So this is their model. 60 centimeter span, 90 grams in weight, and can do the hovering, indoor, outdoor fly without any difficulty. And most important of all, there is a onboard video. You can see this red dot. This red dot is actually the video hat. So you can take image during his fly. And you can also prolong his fly endurance from 3 minutes into 11 minutes. Of course, 11 minutes may be not enough for the real military surveillance, but it just moved forward a big step from the 3-minute endurance. So you can see I'll show this video about their demo film in 2011. So it's a tailless, the flapping wing flight. Then it's a nano hummingbird. Okay, he take off. Can you see? Very small piece of the machine, flying machine, like a hummingbird. It looks like the real hummingbird. So he take off from the ordinary parking lot. Okay, and you can see there is an image. This image is come from his video, onboard camera, onboard camera. So he can see anything. We can see the picture he taken from his onboard camera. Okay, so hummingbird right now adjust the fly motion and location and try to gradually approach to the entrance of the house. So you can see they can control the MAV in a very delicate way and very precise way without collide to other object or even wall ground. Okay, so it gradually penetrate and into the indoor environment and found, oh, there's a terrorist and also terrorist inside. He convert this and just escape from the indoor to outdoors and tell people, okay, there's a terrorist people inside, you can try to attack it, okay, and land it. So it's their demo video to show, wow, how he can do it, how he can do. Actually, very amazing, right? Very amazing. If you look at how small it is, you will see very, very amazing, very amazing. So U.S. Army, actually they dream about, every soldier, if they have this kind of hummingbird on hands, as a scout, they can help their soldier to protect themselves. When they move forward into next building, before the men move to the next building, they can send out this hummingbird to do the detection in advance and make sure no enemy or have enemy. We can do in some action and then keep forward to the next castle or next building. This kind of application scenario, it seems possible right now. And of course, in Taiwan, several research groups have ever started the MAB project since 2000s, including my group in Tankang University. We also initiate a group to do this kind of job. Actually, I'm very lucky to witness what happened about the microbat in Caltech during 2000 and 2001. I witnessed what happened about the microbat development in the lab of the Caltech micromachining lab. Very amazing. And after they stop the project without any funding, keep supporting, I have ever asked Dr. Tai, can we keep doing this kind of vehicle in Taiwan? You say, oh, no problem, go ahead. But using your local technology, okay, try to develop your local technology. Think about how to keep doing that. So our team at Tankang University developed a 3 generation of the MAV, including the initiator in 2004, Eagle 2, 2006. And after 2007, we started the generation about the golden snitch. And this body weight only 5.6 grams. Minimum wingspan, 20 centimeter. And under the support of the Ministry of Science and Technology project, we not only developed the prototype, we also developed a mass-produced MAV education kit. It's something like a logo kit, we good for education, for elementary school or even the high school student that can practice about this kind of, not toy, actually it's an education kit for them to know what is the MAV, golden snitch. And the longest flight endurance about the modified golden snitch get up to 8 millimeter. Of course, compared to microbat, our endurance is a little bit longer because we have some lightweight policy, weight reduction policy, and we also adopt a very lightweight component after 2007. Basically, what is the mission or what is the vision of the MAV? Actually, whatever drone, a manned air vehicle or MAV, they can effectively extend our physical presence to a longer distance. It means that, for example, we cannot go to 500 meters ahead of us, right? But we can send a drone over there, and they have a camera, so they can take image of over there and send back the image. So it's something like we are there. Very similar, we are there. We know what happened in the place. Actually, we are not present over there. So we extend our physical presence. And for the drone and the MAV, countless the MEMS sensor and the actuator are embedded inside drone. Without the help of the MEMS sensor and actuator, how to make the smallest or miniaturization of the manned air vehicle is very, very difficult. But right now, you can buy all kinds of sensor and actuator on board, even camera on board, battery on board, everything on board. Even the CPU we can make on board. So we can make it very smart right now, very, very smart MAV right now. Thanks the help from the mobile phone technology and the MEMS. Okay, and the next topic is how to design. How to design the flapping wing. Of course, in this course, I don't want to talk too deeply about the principle, working principle, or the theory. I just let you have some idea about the biomimic. Learn from nature. Biomimic. So we want to learn from nature. Okay, it's our first rule for design, even for the flapping wing, MAV. If we only do the artificial MAV, we have no previous successful exam. For example, Brother Wright, they have no previous successful example. They must try and error. But our case is not fixed wing. We are flapping wing. So we can learn from nature. Birds, bat, all kinds of fly animal all over the world. So we can observe. So thanks to the effort from the biologists, they provide us a lot of valuable information. For example, here we call it the scaling law. This is the scaling law between the wingspan and the body mass. So you can see bat, small bird, large bird, all their features are lump sum summarized in this straight line. Very interesting. All the fly animals, they have the similar fly behavior. They obey this law. They obey this law. Very interesting, huh? Very interesting. And this law is, we call it the power law. You can see the wingspan have the power law of the mass with a power about 0.39. They summarize from the data. Biologists, they spend several tens of years to collect many data, and we can do the recursal now try to summarize and have the empirical formula like this. So it means that if we can use this formula to predict what the relation between them. It means that, okay, for example, if we want to have the wingspan about 20 centimeter, and actually it's a 0.2 meter. So it's something like this range. So we have the wingspan in this range. So you can see the body mass is probably around 10 grams. Probably about 10 grams. So you have the first design. You can roughly think, okay, you want to have our wingspan about, for example, DARPA, they asked the 50 centimeter, right? You can also apply this formula. But right now, if we make it a little bit bigger, 20 centimeter in wingspan, the affordable total mass about this artificial ornithopter or flapping wing only 10 grams or 11 grams, very, very less. But you have idea. So engineers have this idea, they can start to do the design about the details. Even for the scaling law, actually it's for the flapping frequency. Not only you have the wingspan and the wing and the body, you must let it flap. So we need to have some mechanism can transfer the power from the electrical motor into our flapping wing to do the flapping. So one question comes, what is the wing beat frequency? Or what is the flapping frequency? How fast it should be? So very lucky. Biologists provide us information once again. So we have the scaling law about the natural flapping frequency, not flapping frequency. So very amazing. Many fly animals, they are a little bit diverse, but they still have some train about this. They have power law. They also have the power law. So similarly, when we know our total mass is 10 grams or 11 grams, we can apply this formula to see what the frequency should be. So as I point out, you can see right now the body mass is around 10 grams. 10 grams is 0.01 kg. So you can see the flapping frequency is roughly between 10 to 20 hertz. Probably about 15 hertz. So you have an idea. Not only you make it very light and small, but you also need to make it flap very fast. If very small frequency, not useful. Okay, so this is the usage about the scaling law. We learn from nature from this law. We just not arbitrarily select a spec. We have some basis. This basis can give us a good guideline at the first end. Okay. So let's consider total mass distribution of the 20 centimeter wingspan flapping wing we made. This global, roughly sketch about our MAV. So you can see we have the motor, with a battery, with a control chip, and we have pressure sensor, we have rudder, and we have the flapping wing. And actually, we also have the mechanism for flapping. We will talk about that in the later. So you can see totally, we try to integrate everything together. Not easy, but feasible. And we use the CAD tool, try to do the detailed design. So you can see these are our wing, tail, body, and the inside part you can see the mechanism, motor, control chip, battery, and so on. So everything lump sum together, total mass. You should try to control it properly about 10 grams. It is not a mission impossible, but it's a mission of difficulty. It's a difficult mission, not impossible mission, but difficult. Okay, most important word is, most difficult one, for our experience is how to develop a good mechanism. Good mechanism. Because at that time we can buy everything, thanks to the mobile phone technology and the mass, we can buy almost everything, but only one thing we cannot buy. What is it? Mechanism. Yeah, it's just mechanism. How to buy the mechanism? Nobody can provide you. So we need to develop it by ourselves. And this part is exactly a mechanical component. It's not the electrical. It's not the matter about the microelectrical component. It's a mechanical component. So it matches our expertise. If mechanical background doesn't provide this kind of mechanism, we cannot do anything about the flapping wing. So if you look at this, you can understand why flapping wing researchers, most of them come from the field about the mechanical engineering or even the aerospace engineering. And so we use the plastic injection molding process and facility outside to help us to make this flapping wing mechanism. This mechanism is not very difficult. For design, only 4-bar linkage. Everybody can know how to do the, in the mechanical field. Even the UG, undergraduate student, what is the 4-bar linkage. But the problem is how to make it small. And the light, how light it should be, For Caltech's microbat, the total mass of this mechanism is only 2.8 grams. But for our case, actually, we could try to decrease the mechanism mass down to 1.2 grams. Very, very less. We can make it very small. How can we make it? Because we use the plastic injection molding. This process is very common, very often in the field of the manufacture. Do we ever heard the Foxconn company? It's a foundry company for Apple, for making the case, mobile phone case for Apple. If you look at the mobile phone case, very complicated. And Foxconn company, they can make it very cheap and very accurate and very reliable. They use the plastic injection molding process. So similar, we adopt this kind of technology, try to target the problem about the mechanism, flapping mechanisms. So with the effort probably about 3 years, trying and error, we finally make this mechanism into a reality. And all the MAV developed by our university, actually I show once again about here. So especially about this modified golden snitch. The mechanism actually is used, this plastic injection molding plastic mechanism. And it can create longest endurance about 8 minutes, 480 seconds, with only one time the charging. Of course, it's still far away from the ideal. The ideal flight-induced endurance should be about 30 minutes. Still a long way to go. But we're still waiting for the advanced technology about the battery. In the future, we can have the better lithium battery or even solar panel or other kinds of, any kinds of the power source. We can extend our flight endurance even more. Okay, here we have the introduction video about 6 minutes. I hope you can enjoy this video. Have some music. You can say the Wright brother, right? His invention, man's first aircraft in 1903. But at the time, the fixed wing aircraft. So our group tried to develop the flapping wing. Actually, we are just learned from Caltech. We're trying to make our own model, golden snitch. Also, this is microbat, and this is another kind of MAV developed by other groups in the world. And this is our golden snitch. First generation initiator. Only fry for several seconds. Not very nice, but prove the concept. Prove the concept. Second generation equal 2. We try to do some weight reduction and increase the frapping frequency as well. This is our campus, Tankang University. So we test in our campus. This is my student, Dr. Xu. He created the longest endurance, probably about 30 seconds, regarding this model. This is another one, equal 2. So right now you can see he can fly for a longer time. The lift force right now is more sufficient than before. The third generation, Golden Snitch, we move to another new age because we have the better mechanism developed by ourselves. So we can do the dive-like takeoff. You don't need to do the hand shooting. It can take off by himself. We will also embed some LED as an indicator and let you know what is the trajectory about the flapping wing. So you can see the figure 8. You can see the figure 8, right? The figure 8 shows the thrust force. Thrust force is very huge. So it's a refract about this figure 8 flapping. So in very tiny, very limited space, you can still doing the flight. Full visualization in the wind tunnel. So we release some smokes, and you can see some flow feature, right? Around the flapping wing. We use high-speed camera to take the image. In the following, how to design and manufacture. Okay, so CAD right now is a very popular education, and all our UG students and PG students know how to do the CAD design. Okay, design and simulate, and then send to manufacture. This is plastic injection molding, mold flow simulation for plastic injection molding. So we can simulate and find the best parameters about the manufacturer. And this is the impact simulation. And this is the mechanism motion simulation. So many simulations you need to do. Very interesting. Very interesting. Okay, this is a plastic injection molding machine. Very costly, but we don't buy it. We ask for outside help. Outside company that can provide this kind of service. But we need to do the mold design by ourselves. Okay, you can see it's a fresh, just a fresh component come from the machine. Even for the body we use the EPS, expandable polystyrene body, very light, but very robust. And this is the remote control. My student, Mr. Chen, he controls the flapping wing very well. So you can not only control it, fly in the sky, you can control where it goes. Fly like a real bird, or even a real bat, Yeah, this is what we have ever done before 2010. We have ever developed some, this education kit for high school student or even the elementary school student to practice. So a lot of students of mine devote themselves in this project thanks all of their help. Of course, I need to thank the support from our National Science Council. Actually, it's our Ministry of Science and Technology, actually. Yeah, this is the ending of the video, but not the ending of my talk, okay? Take it easy. But anyway, you can see a lot of work needs to be done in this kind of MAV. Very interesting, but very laborious, actually, I can tell you. I have ever supervised more than 40 postgraduate students about doing this kind of job in the past almost 15 years, I believe. Some of them focus on manufacture, some of them focus on design, some of them focus on flight test, wind tunnel test, high-speed camera test, and even the trajectory analysis, or even the computation fluid dynamics, and even the control chip design, and how to do the, right now we can do the, not only the remote control, but we can also do the autonomous flight control. Today we have no time to talk about this too much. But the autonomous flight control, it means something like the real MAV right now, or UAV right now. We just plan the trajectory about the path in advance in our computer. We assign the trajectory, and the CPU and the MEM sensor on the MAV, they can follow the control of our ground station and to fly according to our plan. So they have the mission, they have the path in the mission. They can do the real fly according to our plan. So take off and cruising, doing some mission, and the cruising back, finally landing. So they can finish the full mission of the drone, like the real drone. But right now, our target, our MAV is very, very small, only palm size, only this kind of palm size. So it's not the magic. We just try to make our dream come true by the available technology we have. So I hope I would like to give a conclusion about the MAV. When I was an elementary school student, I had ever witnessed some RC control player. They try to play with their remote control fixed wing aircraft, in the sky. At the time, very costly. One piece of the RC control aircraft may be equal to 2 months of the salary of the engineer. So very costly. So when I was an elementary school student, impossible for me to buy one of the RC toy. It's too costly. But I just dream. If in the future I can try to, if I'm strong enough, and if I'm intelligent enough, I can try to develop my own unmanned air vehicle. And even I can help other elementary school students or high school students to play with this kind of UAV or drone. It's my dream. After so many years of effort, and many people help me, and also our government, most Ministry of Science and Technology also support us. Taiwan University also support me. Many support. We integrate together, and finally, we can make this golden snitch come into a true product or true UAV can fly. So this is is for my scientific interest, actually. But maybe some people will challenge us. What is your practical use? Okay, scientific interest, very interesting. But what is your practical use in the future? Now our answer is very similar to U.S. Army answer. U.S. Army say, we can do the military surveillance. Okay. But maybe you can say, oh, we are not soldier. We don't need this kind of the mission. So what you can offer us? Of course, you can have other application in amusement, education, right? And maybe in agriculture, monitor, maybe we can try to control insect, control some bad insect, right? Many are possible, or even for the ecological observation, some bird very precious. Maybe we can send our prepping wing drone to observe what happened about their proliferation. If you send the flapping wing or rotary MAV to there, just shock them and frighten them, they will just go away. You don't know what happened about their current situation. But if we send the flapping wing, because very similar to them, so maybe we're not frightened then. So it's good for our observation. So many possible applications, but need our interest and our concern. I think even now, it's not an overall global market product right now. But I think we're still satisfied about our own children because we can try to do something fit our dream. But I think with this kind of emotional encouragement inside ourselves, we can keep moving to find more application in the future. Yeah, don't forget, our MAB project, our MAB is trying to extend our physical presence to a longer distance. This is our vision. And I believe maybe our MAB cannot prolong our long distance. We cannot prolong very, very long. Maybe only several tens of meters. Or to some dangerous environment we cannot reach. We can let our drone, our MAV, to go over there. But anyway, with this kind of vision, I believe we still have some plenty of room about our emerging application in the future. It's something like, I had ever say, Luban, right? All the craftsmen in China. Luban, he made a wooden flapping wing. And another guy just left and hint, right? Your flapping wing is nothing for use. But Luban actually very satisfied about his achievement. And actually, his achievement actually inspired many people like us. We keep doing this kind of flapping wing drone. And we hope this kind of development will be beneficial to our living in the future. Maybe not very apparent, but everything is come from the scientific interesting firstly. And then we try to find out gradually about the practical usage. So don't left at some research, maybe no use at all right now. No, you look at the micromotor, any use, but most of the people would believe it is a very important technology milestone. If you can make micromotor, you can make many delicate things. Similar, if you can make flapping wing into control, you can have more technology to develop more complicated system in the future. Very hard to say. In the future, maybe flapping wing will fill with us, around of all of us. Yeah, maybe in the future, many flapping wing. You cannot distinguish which is living, which is a real bird, and which is artificial bird, right? Yeah, so it's my point of view. We just do our best to try to develop more advanced technology. This advanced technology, maybe before its practical use and commercialization, maybe we have 10 to 20 years need to endeavor. But I think it is what professor or scientists do in the campus. Yeah, so maybe you are not the college student, but just encourage you have paid some attention about the current development about the advanced technology and engineer. Not good for your common sense, but also good for our if you like this technology, encourage us try to do more. Maybe in the future we can develop some technology really beneficial to human people, and just not to damage our environment, like the carbon emission problem, right? Or many problems right now we face. Maybe we can try to reduce the problem. We can try to go enhance about our living, more prosperous and safe and happy. Okay, thank you for attention. This is what I want to talk to you, share with you today. And I hope you would like my teaching video. And we're just looking forward to see you in the future. If you would like to visit us, we welcome you very much. Tankang University is a good university in Taiwan. We have many international international students in our campus. Probably about 2,000 foreigner students here, and we have many sister university all over the world. And yeah, if you have any question, I welcome you to share with us. We can try my best to answer you. Yeah, we still have one session about the Q&A. So if you have any question, don't hesitate to contact me. Yeah, I believe I can provide you some answer and some information. Yeah, good to you understand. Okay, thank you for your attention. I have the I hope you have the enjoy good time in this summer course. Okay, see you later. Yeah, bye bye.